When it comes to solving a system of equations using a matrix, we want to focus on working toward putting the matrix into reduced row echelon form. So in this particular video, we're going to talk about row echelon forms, specifically row echelon and reduced row echelon forms. And in order to do that, we're going to need to follow a specific set of steps, and so we're going to go through these in detail. To put a matrix into row echelon form, we have to meet three criteria. In other words, a matrix is in row echelon form when it meets these three criteria. The pivot entries are equal to 1, and we'll talk in a second about what a pivot entry actually is. If there's a full row of zeros, it's at the bottom of the matrix, and the pivot entries follow a staircase pattern. If the matrix is in reduced row echelon form, that means that it meets all three of the requirements for row echelon form. So its pivots are 1, the 0 rows are at the bottom, and the pivots follow a staircase pattern. And in addition to all three of those criteria, each pivot is alone in its own column, meaning that there are no other non-zero entries in the column that contains the pivot. Now, of course, we don't really know what any of this means yet, so let's walk through an example so that we can talk about each one of these in detail so we understand how to put a matrix into row echelon form and then into reduced row echelon form. And what we're going to see by the end is that getting the matrix into reduced row echelon form is going to be hugely beneficial for finding the solution to the system, because we're going to be able to pull out the solution directly from the matrix. In other words, we're going to be able to just look at the reduced row echelon form matrix and immediately know the solution to the system. So that's why these forms are valuable and interesting to us. So let's say that we're starting here with a matrix that represents a linear system, and it can be an augmented matrix or not an augmented matrix. Let's go ahead and just say that this one is augmented, so the left side here has columns for x, y, and z variables, and the right side represents the constants in that system of three linear equations. Let's talk first about pivot entries or pivots or leading entries. So a pivot is the first non-zero entry in each row. So in this case, as the matrix stands right now, -1, 3, and 1, all down the first column here, are the pivot entries for each row, because each of them are non-zero and they are the first non-zero entries in each row. If this 3 here were a 0 instead, then this 1 here in 2, 2 would be the pivot entry for the second row, because you would have 0, 1, and this would be the first non-zero entry in the second row, so it would be the pivot in the second row. So the pivot is the first non-zero entry in each row of the matrix. To get the matrix into row echelon form, we need all of the pivots to be 1. We also need the pivot entries to follow a staircase pattern. So here, as the matrix stands right now, all of the pivots are in the first column. What we need them to do is stair step down from the upper left-hand corner to the lower right-hand corner, such that each pivot entry is in a new column to the right of the pivot entry in the row above it. So if our pivot entries were here where the -1 is, here where this +1 is, and here where the 0 is, and we had pivots like that, 1, 2, and 3, that would follow a staircase pattern, because each pivot entry would be in a new column to the right of the pivot entry in the row above it. That's what we mean by the pivots following a staircase pattern. So we're going to need to figure out how to do that. And if we end up with a full row of zeros, so we have zeros all the way across, 0, 0, 0, 0, if we're working with the matrix and we get to that point with any row, we need to go ahead and switch some rows to move that 0 row to the bottom. And if we have multiple rows of zeros, we could have none or 1 or more than 1, it doesn't matter. But however many 0 rows we have, any ones that are there, they all need to be moved to the bottom of the matrix. If we can meet those three requirements, then we've got the matrix in row echelon form. So we'll go into this process in much more detail and actually talk about the algorithm that you'll use, algorithm meaning a repeatable process that you cycle through over and over again. You keep following the same set of steps or the same set of rules to get a matrix into row echelon form and then reduced row echelon form. So we're going to talk about that cycle of steps later on. But for now, let's just look at this particular matrix and figure out how to get it into row echelon form. So the first thing is we need all the pivot entries to equal 1. So let's go ahead and first multiply through the first row by -1, because that'll give us a +1 here in the 1, 1 position, which is what we want. We need all the pivots to be equal to +1. So if we multiply through by -1, we're going to get here 1 and then 0 and then -2 and then -1. And then we'll leave the other two rows the same. So 3, 1, 1, -2, and then we have 1, -4, 0, and 2. The next thing that we want to do is get zeros throughout the rest of the first column. This is the beginning of the process we want to use every time. We want to get that +1 in the 1, 1 position if we can, and then we want to zero out the rest of the first column. So we could zero out this entry right here, 2, 1, the 3, by subtracting 3 of row 1 from row 2. In other words, we'll take row 2 minus 3 times row 1 and replace row 2 with that value. So here's what that would look like. We'll leave the first row alone, so 1, 0, -2, and then -1. 3 minus 3 times 1 is 3 minus 3, or 0. 1 minus 3 times 0 is 1 minus 0, or 1. 1 minus 3 times -2 is 1 minus a -6, or 1 plus 6, or 7. And -2 minus 3 times -1 is -2 minus -3, or -2 plus 3, which is +1. Then to get a 0 here in the 3, 1 position, where this 1 is, we'll just take row 3 minus row 1. So 1 minus 1 gives us 0. -4 minus 0 gives us -4. 0 minus -2 is 0 plus 2, or +2. And 2 minus -1 is a 2 plus 1, or 3. And so after those couple of row operations, we now have the pivot 1 in the first column here, and we've zeroed out the rest of the first column. We also can see that the pivot in row 2 is already a +1, and it's already to the right of the pivot in the first row. So we've got this staircase pattern going, and we're doing well. All we want to do now is zero out the rest of the second column. We already have the 0 here in the first row. We need to get a 0 here in the third row where this -4 is, in the 3, 2 position. That means that the first and second row are going to remain unchanged. So we'll say 1, 0, -2, -1, and then 0, 1, 7, 1. And then we'll add 4 of row 2 to row 3. So we'll say 0 plus 4 times 0 is 0 plus 0, or 0. -4 plus 4 times 1 is -4 plus 4, or 0. 2 plus 4 times 7 is 2 plus 28, or 30. And 3 plus 4 times 1 is 3 plus 4, or 7. So now we have the rest of the second column zeroed out other than the pivot entry there. Now at this point, we have pivots of 1, 1, and 30. They are the first non-zero entries in each row. The pivots follow a staircase pattern, and we don't have any 0 rows, so we don't have to worry about moving those to the bottom. The only thing left we have to do in order to get this matrix into row echelon form is to make all of the pivots +1. We already have the first 2 at +1, which means we just need to divide through this third row by 30. To get 30 divided by 30 is 1. That would be the same thing as multiplying the third row by 1 over 30. So if we do that, we'll get 1, 0, -2, -1, 0, 1, 7, 1. And then 0 divided by 30 is 0. 0 divided by 30 is 0. 30 divided by 30 is 1. And 7 divided by 30 will leave as 7 over 30. So now we have 3 pivots. They're all equal to +1. We have no 0 rows, so we don't have to worry about moving those to the bottom. And the pivots follow this staircase pattern. We can think about this as a set of stairs that move from the upper left to the lower right. So at this point, we have the matrix in row echelon form. We often write row echelon form as just REF, row echelon form. So this right here is our row echelon form matrix. Now we could choose to stop there if we wanted to. And this row echelon form matrix would actually allow us to find the solution to the original system of linear equations pretty quickly. Because remember, if these columns here represent x, y, and z variables, and then you have the constant, which will say capital C there, what we have once we get the matrix into row echelon form is we have 1 times z equals 7 over 30. So we have z equals 7 over 30. We already know the value of z. Then we could take that value and plug it back into the second row here, because the second row says y plus 7z is equal to 1. So if we plug in 7 over 30 for z, we'll just have y plus 49 over 30 is equal to 1. In other words, we'll have an equation in terms of just y that we can solve for y. Then we'll have the values of y and z, and we can plug those into this top equation, 1x plus 0y minus 2z is equal to negative 1. We can plug in our values of y and z and solve for the value of x. So row echelon form already makes finding the solution of the system much easier. If we want to go further, we can do a little extra work on the matrix to get it into reduced row echelon form, and then we save ourselves the time of finding the solution, pulling the solution out of the matrix. And the way that we do that is by getting the pivots alone in their own columns, meaning making sure that the pivot entry is the only non-zero entry in its column. We've already done that for the first and second columns. The pivots are by themselves, they are the only non-zero entry in their columns. If we do that for the third column, we'll be done. We'll have the matrix in reduced row echelon form, and we'll be able to pull out each of the values of x, y, and z directly from the matrix. So to do that, we continue with similar row operations that we've been using. We want to first get rid of this negative 2. We want to zero that out. And to do that, we can add 2 of the third row to the first row, because when we take 2 times 1, we'll get 2. When we add that to negative 2, we'll get 0. So for the first column, we'll say 1 plus 2 times 0 is 1 plus 0, or 1. 0 plus 2 times 0 is 0 plus 0, or 0. Negative 2 plus 2 times 1 is negative 2 plus 2, or 0. And then negative 1 plus 2 times 7 over 30 is negative 1 plus 14 over 30. So negative 1 plus 14 over 30. We can rewrite that as negative 30 over 30 plus 14 over 30. And we get negative 30 plus 14 is a negative 16 over 30, which is the same as negative 8 over 15. So we'll put that in as negative 8 over 15, and then we'll leave everything else the same. So 0, 1, 7, 1, and 0, 0, 1, 7 over 30. Our last step will be to zero out this 7 so that this pivot entry here is the only non-zero entry in its column. So to zero out the 7, we'll take 7 of the third row away from the second row, because when we take 7 of the third row, we'll get 7 times 1 here is 7, and then we'll say 7 minus 7 and get 0 right here. So when we do that, our first row will stay the same, 1, 0, 0, negative 8 over 15. The second row here will take 0 minus 7 times 0, 0 minus 0 is 0. 1 minus 7 times 0 is 1 minus 0, or 1. 7 minus 7 times 1 is 7 minus 7, or 0. And then 1 minus 7 times 7 over 30 is 1 minus 49 over 30. So 1 minus 49 over 30. That's the same as 30 over 30 minus 49 over 30. That gives us a negative 19 over 30. So we'll say negative 19 over 30. And then the third row stays the same, 0, 0, 1, 7 over 30. So with the matrix in this form, let's check this against our list for reduced row echelon form. We still have the pivots are all equal to positive 1. We have no 0 rows, so we don't have to worry about moving those to the bottom. The pivots do follow a staircase pattern. We can see that we still have our staircase pattern, and each of the pivots is the only non-zero entry in its column. All the other values in the pivot columns are zeroed out, which means that this matrix is in reduced row echelon form, and we often call that form RREF, reduced row echelon form. So this is our reduced row echelon form matrix, and the reason that it's helpful to get the matrix all the way to reduced row echelon form is because now it's really, really quick to pull out the solution to the system. Remember that these columns represent x, y, and z variables, and then the constants over here on the right side. So literally, once the matrix is in reduced row echelon form, we have the solution to the system of linear equations. We say 1x plus 0y plus 0z is equal to negative 8 over 15, or in other words, x is equal to negative 8 over 15. Y is equal to negative 19 over 30, and z is equal to 7 over 30. So instead of using substitution and elimination and graphing and going through lots of steps to try to find the solution to the system, in 6 matrix steps, we were able to get the solution to the system. And while this might feel tedious and confusing right now, and may not seem faster than the methods we used to use, as you get comfortable with these row operations and using matrices, you'll find that this process goes much, much faster than the old methods we were using, especially as the system gets larger. It's one thing to use substitution, elimination, and graphing to solve a system of 3 linear equations in terms of 3 unknowns, but when you have a system where you have 20 equations and 20 unknowns, using the matrix method is going to be significantly faster than one of the other methods. So the bigger the system, the bigger the time savings when you're using a matrix instead of one of those other methods to find the solution to the linear system.